start the recording. Okay. Well, really, it's the second third of section 2.5. We're never going to get to the decimal representation stuff in that section, but I recommend reading it anyway. So our topic today are nested intervals. So let me start with a more general definition. So the sequence S1, S2, and so on of sets is nested if, well, they have to they have to nest, but there's two ways they can do it. Okay, they could be nested increasing or nested decreasing. Okay, and that's weakly increasing and weakly decreasing. Okay, that's just general mathematical definition that comes up in all the math classes. Today we're interested in nested intervals, and they're all going to be nested decreasing because that's the theorem we're going to prove. Okay, and it's a cool theorem that is pretty useful and also foreshadows some stuff from the second semester. So let's start with an example. So let IN be the closed interval from 0 to 1 over n. Okay. Then, that is a nested sequence of intervals. I1 contains I2, contains I3, and so on. And our question is, what is their intersection? And that would be the intersection. Okay. Well, volunteers?
0.
Yeah, the set consisting of 0. Yep, there's just 1 point in there. Okay, so we claim that this intersection, and just to be, we don't need these INs hanging around. This is just the set 0. Okay, we're trying to prove a set equality, so we're going to have to prove both directions here. First, why is 0 in there? It's just to see if you're awake yet.
0's in every interval.
Yeah. It's in all of them. That's the definition of intersection. Okay, now, why isn't anything else in there?
Because we can always pick a smaller number, and then we use that one theorem, I don't remember what it's called, where the number is between 0 and an arbitrary real, then you can make it 0.
Yeah, so we saw something 2 lectures ago that's helpful here. You got to be a little bit careful. There's actually a little bit of a catch to the proof here. You want to use the fact that for any real number, there's a number of the form 1 over n that's smaller than it, right? Yeah, you just got to be careful that real number has to be positive. So technically we should eliminate the negative numbers separately. Okay. If x is less than 0, then x is not in, well, let's just say it's not in the first one. So it's not in the intersection. Okay. Now suppose take some x greater than 0. And we could open up the book and try to find the actual theorem statement that we're going to use, but that's a waste of time for everybody. This is just a fact, so we know there is some natural number little n, so that 1 over n is less than x. Therefore, x is not in the intersection. Okay. Let's just, I guess if we're gonna, we can call it a proof and we put a QED at the end. Okay, any questions?
So if we're writing this for like a homework, should we put a conclusion, like, using the trichotomy, therefore 0 is the only thing left? Or is that just enough, like, by that?
I think that's a personal decision.
Okay.
If you think it reads better with the trichotomy at the end, that's fine with me. I'm pretty convinced by what we got there already. Okay. Any other questions? Okay, we're not going to prove any more examples, but let's just state some. That was example 1. Example 2. Let's do the intersection. So we're gonna look at these. We're not gonna prove them. Maybe we'll talk about proving them. What would be the intersection of those half open or half closed intervals?
Still 0?
Yep, still the set 0, because 0 is still in all of them. That's one way to get it from example 1, is just say, well, 0 is still in the intersection. But these sets are strictly smaller than the sets in example 1, so they'll have a smaller, they'll have a weakly smaller intersection, right? Okay, what if we put the half open thing on the other side?
Empty set?
Yep, that's the empty set. You can get that straight from example 1 too. Now 0 isn't in any of them, and all of these intervals are contained in the example 1 intervals, so they couldn't have anything else. Okay, let's get away from this just a little bit. Here's something. I should have put one of these in the homework. I just forgot to think to put one of these on the homework. But anyway, what's this intersection?
Is it the closed interval 0 to 1?
Mm-hmm. Perfect. Yeah, that's in all of them, and then you see that these, the minus 1 over n's are going to 0, and the 1 plus 1 over n's are going to 1. That's not the proof, but, right? Now, if you wanted to prove this one, and this is the one I should have put on the homework, you would take a negative number and you'd show that eventually this minus 1 over n is greater than your negative number. That follows from the fact we used earlier. And then you take a number greater than 1 and you'd show that eventually this 1 plus 1 over n is less than n. Okay? Good. Any questions?
If we open the interval on both sides, is it gonna be the same still?
So if
Right,
we open
yeah.
this guy, yes. Yep. Still, and you think about it, still the closed interval from 0 to 1 is in this intersection because it's in every one of those open intervals. Yep. Okay, so now here's our big theorem. This is a really important property of the real numbers. We're going to call it the nested interval theorem. Now, our book calls it the nested interval property. I know why they're doing that. They're doing that because they're saying that, well, I mean, they're not saying it. This is equivalent to the supremum property. That's why they're calling it a property. I'm going to call it a theorem, just to have, it's a consequence of the supremum property, the way I'm going to present it. Okay. Suppose that you have a nested decreasing sequence of sets. So this is a nested sequence. Okay. Now I'm going to add some hypotheses on these sets. In the book, they say that they're bounded and closed. I'm going to add that they're also non-empty. So they're non-empty, bounded, closed intervals in the real numbers. Then your conclusion is the intersection is not empty. Okay.
Quick question. Is
Yeah.
it possible to have closed intervals that are empty?
Yeah, we talked about this at the end of the last lecture. The empty set is a closed interval
Oh, right. Yeah, okay.
because the empty set contains none of its endpoints.
Right, okay. Thanks.
Now, what's going on in the book is at some point they thought that they're just not going to allow the empty set to be an interval. I believe. And that's why in the book you see this property stated and they don't include that word non-empty. I think because they just said intervals can't be empty. Well, we're going to say intervals can be empty and we're going to be careful here. Okay? Okay, so one of the parts, so in the homework, number 2 on the homework asks you to show that each of these 3 hypotheses is necessary. So it asks you to drop one of them and find a counterexample. Okay? Okay. Let's prove it. Okay, it's our big theorem today. Well, it's our first big theorem. Our second big theorem is that the real numbers are uncountable, which actually comes out as a consequence of this. Okay. Since each interval in is bounded and closed, let's give their endpoints names, okay? So we can define real numbers. They're going to be, we'll call the lower bounds A's, and we'll call the upper bounds B's, so that, well, just there you go. So that the intervals are the closed intervals from AN to BN. Okay. Let's draw a picture. Okay. Okay. That would be a picture of the first interval I1. Okay, it goes from A1 to B1. Now they're nested decreasing. So what we think, well, I mean, not really think, I mean, so A2 is going to be to the right of A1, and B2 is going to be to the left of B1. But I really mean weakly to the right and weakly to the left. I guess the proper way to say this would be A2 will not be to the left of A1. It could be A2 could equal A1, right? Okay, and then we'll have an A3 and B3, and that's what they're going to do. And the theorem is saying, at the end of the day, there's some point in there, in all of them. Okay, what does this picture suggest to us? This says that it looks like all the A's are less than or equal to all the B's. Okay. See, I am using our logical symbol there because that is not part of the formal proof. That is just our intuition that we're doing off to the side, okay? Okay, what would it mean? Well, okay, let's check this, okay? So we claim that AM is less than or equal to BN for all M and N at least 1. Suppose otherwise, or suppose to the contrary, that we broke this. So what would that mean? Some AM is greater than some BN. Okay. Okay, we're going to show that this is a contradiction. Okay, what's the problem? Let's do a little picture to see where the problem is. If your AM is over here and your BN is over there, okay, the problem is the BN is the right end point of his interval, and the AM is the left end point of his interval, his or her interval. Well, this is a problem, right? What does this contradict?
The subsetness.
The nesting.
Yes.
Yes. So, however, then we would have A n is less than or equal to Bn is less than Am is less than or equal to Bm. So the intervals wouldn't nest. So we have proved, well, I'll just write the conclusion here. Therefore, we have our inequality. Okay? Now, you think about this from the perspective of suprema. This shows that every B is an upper bound on all the A's. Okay? In particular, the set of A's is bounded above. Okay? So this implies that the set of all the A's is bounded above. Okay. It's also non-empty. There's at least one left endpoint, A1. Okay, all the other A's could be equal to A1, but there's at least one thing in that set. So, we know that it has a supremum. Let's give that supremum a name. X. Okay. Now we know that well, this is an upper bound on the A's. So we know that AN is less than or equal to X. That's just silly. We wouldn't have to write that. But I further claim that X is less than or equal to all the BNs. Why is that true?
It's true because if there is a BN less than X, then we would have an AN in A which is greater than BN.
I agree.
Isn't that one of the theorems that we had, or one of the properties of the supremum?
Yeah, I agree. I think there's just a slightly easier way to do it. Oh, yes. So properties of the suprema. That's where I want to go. All of the BNs are upper bounds on the set A, and X is the supremum, so it's less than or equal to all the upper bounds. Okay, because X is sup A, and all the BN each BN, let's say, is an upper bound of A. Okay, well, what have we shown? We've shown that it's in all these intervals, right? Therefore, X is in A and Bn for all n at least 1. So X is in the intersection. This was IN, which proves the theorem. Okay. Any questions on the theorem?
Can we do the same thing with infimum?
Sure. Yeah, we could look at the infimum of the B's instead.
Okay.
It'd be the same thing. Yeah, so just to, the proof was kind of long, but that's because we wrote out a bunch of steps. The point was, first we had to, first thing we had to do was introduce some notation so we could actually talk about these endpoints. Then we established that they behaved like our picture said they did. Okay. If you were completely lost in this proof, I would say drawing that picture is pretty important, so you can see what's going on. That red dot in that picture, that is X. Right? It's the supremum of the A's. Okay. And then once we got that, we were allowed to define X to be the supremum. And because of the properties of supremums, that gave us that it's in, that point X is in all the intervals, so it's in the intersection. Okay? Now, this theorem is not true for the rational numbers. Okay, this nested interval theorem. I should put that on the homework too. Wow. I'm having all these regrets about that homework I gave you. Why isn't this true for the rational numbers? I'm going to come up with a sequence of non-empty bounded closed intervals. There you go.
So,
why?
I've got a question about that.
Yep.
When you talk about saying in the rationals, how come you can use the square root of 2 in defining this interval?
That is a really good question. And I think what I need to do here is, well, here, I'm just going to rewrite it. I think that's a really good question. What I should do is intersect them all with Q. Now these are intervals of rational numbers.
Okay, that makes sense. So you're defining your interval to trick the rational numbers and then throwing away all the real ones?
Yep.
Okay, that makes sense.
And these are still non-empty,
Right.
because the rationals are dense. This is a result that's in the book that we didn't explicitly prove, but the rationals are dense, so there are going to be rationals in that interval for all n. Okay? But you see, I mean, the only, if you looked at this in the real numbers, the thing in the intersection would be the square root of 2. And obviously that's not a rational, so it's not there. Okay? Good. Let me emphasize again, though, in this class, unless it's specifically said we're working in the rationals or something, we're in the reals. Okay, for this semester. Next semester, we're going to be all over the place. But for this semester, it's always the reals. Okay. Oh, we talked about the length of an interval last time. I mean, it's just the difference between the endpoints, right? These guys are bounded, so they all have finite length. Just pointing that out. You can show, using essentially the same proof, that if the lengths, you look at the lengths of these intervals, if those lengths go to 0 as a sequence, then there is precisely one thing in the intersection, and that one thing in the intersection is X. Okay? That would be how that would be one way to prove that this intersection, in the reals, it would only be square root of 2, because those lengths are going to 0. Okay, the other way to prove this would just be to go back to how we did example 1 and do it that way. Okay, so now we're going to use the nested interval theorem to prove that the reals are uncountable. We need a lemma for that. So our lemma is a little technical, I guess. We're given a closed interval of real numbers. Now, I'm going to say it has non-zero length. I'm just excluding the empty set, I guess. Oh, no, I'm sorry. I'm excluding two intervals that way. I'm excluding the empty set, and I'm excluding singletons. Singletons also have zero length, okay? So I want to get rid of both of those. Now, some people would just say, given a closed non-degenerate interval, that'd be fine too. Okay? And so we're given a closed interval that actually has some stuff in it, more than one thing in it. And we're given a point x in the real numbers. There is a closed subinterval contained in I of non-zero length which doesn't contain x. Okay, do our picture here. There's our real line. There's I. It has non-zero length. It's closed. If x is, say, over there on the left, then the lemma would just say, well, I works, here's I, right? It would just give you I back. So that's not very interesting. But if x is in I, okay, then the lemma says, well, there's a closed subinterval of I that does not contain x. So that would be your J. Okay, that's just all the lemma's saying. I hope it's pretty clear that this lemma should be true, but I hope it's also clear that this lemma requires proof. Okay. So let's prove it. I'm going to say that it suffices to prove the lemma for bounded intervals. I. Why does that suffice? So I'm claiming that if you knew it was true for all bounded intervals, then you would know it's true for all intervals.
I guess you can pick a bounded interval inside of an unbounded one.
Yeah. So if you're given an unbounded one, just pick a bounded subinterval of non-zero length, and then apply the lemma there, and you'll be fine. Okay. Oh, go ahead.
Are the only closed intervals that are not also bounded are the ones with infinity in them, or just the empty set itself?
The empty set's bounded. The empty set doesn't have a supremum or an infimum, but it is definitely bounded.
But a closed non-bounded interval would be something like that includes infinity on the other side.
Yeah. So those are all a infinity or minus infinity a. Those are your closed. Oh, or the real line itself.
So, sorry, I was just going to ask, if you were given an unbounded interval, then the bounded interval that you choose would contain x?
No, so like let's say you want to prove the lemma for this interval that goes from a to infinity.
Mm-hmm.
I would say just okay, we'll apply the lemma to this closed interval from a to a plus 1.
So why does that suffice?
Well, if the lemma holds for a to a plus 1, then it also holds for a to infinity. Because all the lemma's giving you is this subinterval that doesn't contain x.
Okay.
Right? So
Thanks.
you got a subinterval of the little one, that's a subinterval of the big one.
Okay, thanks.
Okay, thank you. The whole reason I want to do this is because I want to have real numbers a and b. So now suppose that I is the closed interval from a to b. Now we consider there's a bunch of ways to do this. Here is my favorite way. I'm going to define I1 to be A2 A plus B minus A over 3. And I2 is going to go from A plus B minus A over 3 to A plus 2 times B minus A over 3. And I3 to B minus A over 3 to B. Okay. Add some punctuation. There we go. Now I made it a sentence. Okay, maybe we should go with the picture on this. We've got an A and a B. I chopped it into thirds. That's it. Okay, so I chopped our closed interval of non-zero length into thirds. Okay. Is there a question? Let me just point out while we're here that B minus A is the length, and you can see that because that's non-zero, these are actually going to be distinct intervals. Okay. Now, I claim that one of those three is bound to work. Why would one of those three be certain to work?
Even if x is the boundary for one of the other sets, it's not going to be in the third.
Perfect. This is
Could we
the...
also say that the intersection of the three intervals is the empty set?
Yes, yes. So no point lies... I actually, that's yes. We'll say it that way. No point lies in all three of these sets. So one of them is certain to work. Let me put it this way. One of them can certainly serve as J. Okay. I think it's not obvious when you look at this lemma And there are other ways to prove it, but I don't think it's obvious that you're going to end up chopping the interval into thirds. But you can't chop it into halves, because if you chop it into halves, that x might be that point on the boundary. Okay. Now, I mean, you could, yeah. I mean, there's plenty of other ways to prove it, but I like this way. I'll just chop it into thirds. One of those has to work. Okay, any other questions before we do the uncountability of the reals?
So back to the lemma.
Mm-hmm.
So x does not necessarily have to be an I. It just has to be a real number.
Yeah.
Correct?
That's correct.